let me ask you a question. Can we exceed the speed of light? The answer is clear. No. Of course, if I just throw that answer at you, you might not be satisfied. We should explain it in more detail. There are many things in physics we are uncertain about, but one thing is beyond doubt: in the universe, nothing, whether it's spaceships or light itself, can surpass the speed of light in a vacuum, which is 300,000 kilometers per second. This number isn't particularly precise, but let's put it into perspective. The fastest human sprinter can reach about 10 meters per second, the fastest cars can go about 340 meters per second, and spacecraft in orbit travel around 8 kilometers per second. That's just 0.0025% of the speed of light in a vacuum. In everyday life, there's no way for you to approach this speed limit. However, this limit exists. It's a rule that cannot be broken, a constant reminder. While the universe is full of strange phenomena, there are indeed things you simply cannot do here. This speed limit is undeniably real. The theory describing it, Einstein's theory of relativity, has been repeatedly confirmed with great precision. The principle that nothing can surpass the speed of light has been deeply embedded in the details of modern physics. If this limit were not true, we would have noticed inconsistencies by now. That's because the speed limit of light is not just a phenomenon, it forms the foundation of many other complex theories and experimental results. If this limit were incorrect, other theories and experimental outcomes would also fail. Yet, with our highly precise measurements, we have not observed any such problems. So, no matter what you do, who you know, or who you are, you simply cannot travel faster than the speed of light in a vacuum. This is one of the peculiarities of our universe. As we'll see, this speed limit leads to all sorts of strange consequences. It not only hinders communication between people in different parts of the universe, but also causes disagreements about the order in which events occur. Moreover, although this speed limit is deeply ingrained in modern physics, it still leaves some mysteries that puzzle physicists. For instance, where does this speed limit come from? Why is it 300,000 kilometers per second? Why isn't it 400,000 kilometers per second or just 3 meters per second? Could this upper limit ever change? Today, we'll explore one of the universe's greatest mysteries. Einstein introduced the concept of a universal speed limit in his theory of relativity, not as a whimsical idea but based on solid reasoning. Why should the universe have a speed limit? Why can't you simply hop onto a rocket, ignite its engines, and accelerate indefinitely to zip across galaxies? If the universe is a vast emptiness, what exactly is stopping you from flying as fast as you want? For an average person, learning that there's a speed limit in the universe might elicit a simple "oh, okay, I get it" without delving further. But for the audience of this program, just knowing the answer isn't enough. We'd rather dig deeper. Why? Intuitively, we think of space as an empty void, so someone traveling through it should be able to accelerate endlessly. But this assumption is precisely the problem. As I mentioned earlier when discussing space, space isn't an empty stage, it's not something you can just zip through. Space is a substance, it can bend, stretch, and ripple. If you recklessly speed through it, it might even get upset. In fact, the universe's speed limit has given physicists a key insight: space is not completely void. If you can shift your perspective and think of space not as emptiness but as a something, it becomes slightly easier to understand why everything within it would have a speed limit. So, what do we know about this speed limit? First, it doesn't directly prevent you from accelerating. Even if you try to exceed the speed of light, you won't suddenly hit a wall, nor will your spaceship's engines explode. If you have a spacecraft and push the throttle to its maximum, here's what will happen: you'll spend an incredibly long time just approaching the speed of light. Even with an acceleration of 10 g, that's 10 times Earth's gravity, or about 100 meters per second squared, the maximum a top fighter pilot can endure, it would take you months to approach 300,000 kilometers per second. During that time, you'd be pinned to your seat, unable to move. After accelerating for a long time, you'd find that you can't travel faster than the speed of light. It's just the way things are. There's no dramatic change, you simply can't reach or exceed 300,000 kilometers per second. You'd go faster and faster, but at some point, you'd notice that accelerating further becomes increasingly difficult. No matter how hard you push the throttle or how long you try, you'd never reach or surpass the speed of light. In mathematics, there's a concept called a limit that can help you understand this. Imagine adding 1 plus 1/2 plus 1/4 plus 1/8 endlessly. What number would you ultimately get? If you're unfamiliar with the mathematical concept of limits, you might assume that an endless addition would result in infinity. But that's not the case. Adding 1 plus 1/2 plus 1/4 plus 1/8 infinitely results in a value that approaches 1 but never actually reaches it, let alone 2. So, when you push the throttle in your spaceship and accelerate continuously, you're facing a similar situation. You'll keep approaching the speed of light but never actually reach it. The fact that the universe has a speed limit is quite strange when you think about it. Imagine that even without any external forces acting on you, something prevents you from going faster. This is a gradual limit embedded in the structure of space-time itself. Whether you're walking through a hallway or driving on a road, it's always at play. This effect exists even at lower speeds, though it's so subtle as to be negligible. However, it does exist. This means that relativity doesn't just apply at near-light speeds, it's always subtly affecting your motion. If you attempt to surpass the speed of light, space-time itself will warp. The universe's speed limit isn't just a simple upper bound or ceiling, it acts as a kind of distortion and is an intrinsic property of space-time. The left-moving photons are also peculiar. You might think these photons would travel slower than the speed of light, specifically, cv, since they are emitted from the Earth, which is moving to the right. However, photons, massless particles, possess a unique property. In a vacuum, they always travel at the universe's maximum allowed speed, never slowing down. Thus, light always moves at the speed of light, no matter who measures it or how fast the observer is moving. This means that if you are floating in space watching the Earth zoom past, you'll observe both photons moving relative to you at precisely the speed of light. Likewise, the hamster on Earth will see the photons moving relative to it at the same speed. Here's something exciting about the universe's speed limit: it applies to relative speeds between objects, not absolute speeds. That's because, in the universe, there is no such thing as an absolute speed. You might think floating in space grants you the authority to determine the pace of motion. But in reality, both you and the Earth are moving relative to other things, such as the Sun, the center of the galaxy, or the center of our galactic cluster. Even if there were a center of the universe, which there isn't, who could determine your true speed relative to it? Absolute speed, in essence, is meaningless. The universe's speed limit dictates that nothing can appear faster than the speed of light to any observer, and this is where things start to get weird. From this point onward, it only gets stranger. Returning to our earlier example, the hamster is moving relative to you, yet both you and the hamster will see light leaving the flashlight at the same speed. That's already puzzling. Now, let's assume the hamster has targets on either side. Which photon from the flashlight would hit its target first? The hamster sees photons traveling in opposite directions at the same speed. Since the two targets are equidistant from it, the hamster would report that the photons hit the targets simultaneously. But your perspective is different. You see both photons moving at the speed of light relative to you, but you also see the hamster and the targets moving together. Thus, when the photons travel toward their targets, you'll notice that one target, the left one, moves toward the photon, while the other target moves away from it. The result? You would see the left photon hitting its target before the right one. In other words, you and the hamster perceive completely different outcomes. The hamster observes the photons hitting the targets simultaneously, while you see them hit in sequence. Strangely, you're both correct. So far, we've only discussed two perspectives. But what happens if we add another observer? Things get even more peculiar. Imagine this: you and your hamster are marveling at the universe's wonders, while your cat is aboard a spaceship flying past Earth. Its direction of motion relative to Earth is the same as Earth's direction relative to you, both moving to the right, but the cat's speed is faster than Earth's. When your cat looks out of the spaceship window, it sees the hamster and Earth moving to the left relative to its spaceship. From the cat's perspective, the hamster's photons still travel at the speed of light, as they must adhere to the universe's speed limit. However, since the Earth is moving left, the cat would report that the right photon hit its target first. Now we have three conflicting reports. The hamster says the photons hit the targets simultaneously. You observe the left target being hit first. Meanwhile, the cat sees the right target being hit first. Yet, all of you are correct. We must not only accept the universe's speed limit but also abandon old notions. We can no longer assume that events are simultaneous for all observers everywhere. Nor can we assume that we can provide a unified description of all events in the universe. While it may seem reasonable, everything depends on which observer you ask and how fast they are moving. And the speeds here are relative, not absolute. All this should make you pause for thought. It means that in the universe, there is no absolute before or after. Two honest observers can describe the same events differently, and yet both be correct. Looking at it from another angle, by moving at different speeds, you can change the sequence of events. Because you, your hamster, and your cat are all moving at different speeds, you perceive the same event occurring in different orders. This defies intuition since we prefer to imagine a unified history of the universe, where all events have a clear and absolute sequence. But in our universe, that's impossible. The concepts of simultaneity and absolute time simply don't exist. This is a consequence of light traveling at the same speed for everyone. At its core, it's because the universe enforces a maximum speed limit. Can we rearrange the order of events? Currently, the most advanced observer is the cat, which sees the right photon hitting its target first. Let's push the limits of imagination. What if the cat's spaceship exceeded the universe's speed limit? What would happen? As the cat's speed increases, the time it observes between the photon leaving the flashlight and hitting the target shortens. At some point, if the cat's speed is fast enough, it would see the photon hitting the target before it even left the flashlight. But that doesn't make sense, it violates causality. We all know that effects follow causes, not the other way around. In a universe without causality, life would be utterly chaotic. Imagine water boiling before you turn on the stove. Just thinking about it feels bizarre. In such a surreal universe, it would be nearly impossible to understand how things happen, let alone establish reasonable physical laws. From this, we conclude that nothing can travel faster than light, as doing so would break causality. Violating causality is no trivial matter. Speed limit origins. Returning to the speed limit, what principle supports it? The simple answer is, we lack definitive evidence proving the universe must have a speed limit. But we have a strong justification: to preserve local causality, a speed limit is necessary. As seen in our earlier experiment, without a speed limit, causality breaks down. Between the necessity of a speed limit and the necessity of causality, causality is undoubtedly more important. It seems to be a reasonable prerequisite for the universe. But note that I mention local causality. By local, we mean that the number of things influencing you is constrained to what's nearby. If there were no speed limit, events from anywhere could instantly affect you. In our actual universe, only events in your vicinity can immediately have a causal relationship with you. For example, even if the sun were to explode right now, we wouldn't know for another 8 minutes. During that time, no one could know that something happened to the sun in any way. With this in mind, the existence of a universal speed limit makes sense. It provides the universe with locality and causality. And that's where we'll pause for now. We've seen how the universe's speed limit shapes the very fabric of reality and learned why nothing can exceed the speed of light. But the story doesn't end here. There's so much more to uncover. In the next episode, we'll dive deeper into the mysteries of light speed, explore its fascinating implications, and answer the big question: can we ever find a way around this cosmic limit? Stay tuned.